So any exponential random variable satisfies this property. We want to prove that similar. I mean, in the discrete case, if a random variable satisfies the multiplicative property or the memoryless property, then it is geometric random variable in the discrete case. Similarly, we want to prove the same thing here. So this is the proposition. If a random variable x satisfies probability of x greater than a plus b equal to probability of x greater than a, probability of x greater than b, then x follows lambda for some lambda. This is what we want. So it's only the exponential random variable satisfies this property. That's what we want to prove. X is continuous. I mean, this is for all AB. It will not satisfy that property. You don't need to have this. X is okay. Okay, let me. Sorry, I forgot to say. We need to have one more one. Let's see. Let X be a. You don't need continuous because this is continuous. When AB this is continuous, then that will follow. X be a random variable such that probability of x greater than 0 is positive. I mean, it's not a negative random variable. It's not a purely negative random variable. It takes some positive values, okay, with positive probability. Okay. Then it is a positive. It's a random variable. It's not a purely negative random variable. It takes some positive value. Probability of x greater than b equal to probability of x greater than d times probability of no plus. That will be the intersection. No, it cannot be that. Okay, then it is exponential random. This is what we want. Okay, so first we have this probability. A, B are greater than 0. Yeah, what else you need? Yeah, we will prove that it cannot take negative values. When this happens, it will not. So this is, I mean, you can assume that it's a non-negative random variable and prove this. But we will prove that it cannot take negative value, number one. Then we will prove this. So first claim is we have probability of x greater than 0 greater than 0. Then claim probability of x greater than 0 equal to 1. It is just clear, right? Probability of x greater than 0 is equal to 0 plus 0 is 0. So probability of x greater than 0 times probability of x greater than 0. Since so only 0 or 1 will takes the value. So this implies probability of x greater than 0 equal to 1. Clear. Okay. So now next claim is probability of okay. So let g of x equal to probability of x greater than x. If we want to prove that we want to prove, I mean not claim, let. Now the claim is g of 1 is less than 0, less than 1, greater than 0. Okay. Strictly less than 1, strictly greater than 0. G of 1 is. Okay. G of x is this probability, then g of 1 is this. Okay. So suppose, I mean, g of x equal to 1 minus f of x, of course. Okay. So suppose g of 1 is equal to 1. Of course, this is a probability. This is a probability. So it has to be between 0 and 1. It cannot take the extreme values, 0 and 1. Okay. So suppose g of 1 equal to 1, then g of n equal to g of 1 times g of 1 times equal to 1 again. Okay. Now g of n goes to 0. As n is greater than 1. G of 1 equal to n equal to 1 also is 1. What is the problem? For any n, this is true. Okay. G of n goes to 0 as n goes to infinity. So this is not possible. G of n equal to 0. G of n is equal to G of 1 times G of 1 times G of 1 because this property. What is it? This but G of n goes to infinity as but G of n goes to infinity. So this is not possible. So not possible. 1 minus f of x. F of x goes to 1. So G of x goes to 0. Okay. As x goes to infinity. So G of n should go to 0. But G of 1 is 1, which is not possible. So it should be strictly less than 1. Okay. On the other hand, so here we have already proved that it's a positive random variables. So I mean, x going to minus infinity does not matter. So we have that limit x going to 0, f of x equals 0. F of x equals 0. Right? Yeah. So if you have g of x, that should be 1, right? Okay. G of x equal to 1. So if g of 1 equal to 0, that's not possible. G of 1 equal to 0, then g of 1 by n times n equal to g of 1. Okay, this implies g of 1 by n is also 0. Okay. 0. But then g of x should, I mean, g of 1 by n should go to, what's the problem? I will write there. Okay, I will write here. There is some space. Is it okay if I write it here? Okay. So this is true. G of n equal to g of 1 power n. Okay. This implies g of 1. This is for all n. Okay, let's forget this. G of nx equal to g of x power n. Okay. And g of x by n equal to g of x power 1 by n. Okay. This is true. Both these things are true. Okay. If you take n times this, you will get this. If you take n times this, you will get. If you take n times this, you will get this. If you take n times this, you will get it. So 1 by n is this. Okay. Now g of from here. So one direction is g of n is equal to g of n is equal to g of 1 power n, which if g of 1 is 1, so I mean it cannot go to 0 as n goes to infinity. Here as n going to 1 by n goes to 0. Okay, so if g of 1 by n, if g of 1 by n equal to 0, if g of 1 is 0, then g of 1 by n is also 0. So it cannot go to 1. So this is also not possible. Any difficulty in this? I'm just using the property f of x as x going to 0 is 0. F of x as x going to infinity is 1. So g of x is the other way. G of x goes to 1 as x going to 0. And g of x goes to 1 as x going to infinity. G of 1 by n, if suppose g of 1 is 0, g of 1 by n is also 0. Okay, because it's just 0 power 1 by n is 0. Okay, so it cannot go to 1. If it is 0 for all 1 by n, it cannot go to 1. Okay, so this is a contradiction. So it's not possible. So these things imply that our proof g of 1 is strictly less than 1, strictly greater than 0. So we have this. G of 1 is strictly less than 1, strictly greater than 0. And we also have G of m by n equal to G of 1 over m by n. Okay. I mean, G of, you know what is m by n. Okay. Now, this e power minus lambda, e power minus x is a function from 0 infinity. I mean, it takes 0, I mean, it goes the other way, 0 to infinity and infinity to 1. So it's a 0. So e power minus x, so there exists lambda real, I mean, lambda positive. I mean, this is a decreasing function, strictly decreasing function. Of course, log is the inverse, so it's invertible. I mean, you take the log, that is the inverse. So hope you know that this is an invertible function. So because of that, there exists a lambda, that is the g of. Okay. We only need to prove g of x equal to minus lambda. This is what we only have to prove this. Okay. But then, so if we call this equation a star, R is satisfied for x equal to m by n. Okay. That is, star is satisfied for x in rational numbers. So for general R, choose n where Rn is rational, because rationals are tens in real numbers. By right continuity, this is right continuous. I mean, F is right continuous, G is also right continuous. Okay. G of Rn will it will increase. F is not, it will decrease. No, from this way it is increase, right? Yeah, G of Rn will doesn't matter by right continuity. So this is equal to G of 1 power. This is just e power minus lambda Rn. This will go to e power minus lambda x. So it is exponential distribution. I mean, from this we can find what is f of x. Okay. We use the right continuity, convergence at 0, convergence at infinity, and the multiplicative property. From that we got this is the only function. And of course, we use the fact that this function is a, I mean, invertible function. Rn is in Q, rational. To have rationals, I mean, this is only right continuous. So you can take rational decreasing to this. Rn, so it should decrease, right? Decrease, sorry. From here, it should be decreasing. I mean, it is not left continuous, it's only right continuous. So that is enough. Okay. Rn decreasing to x. And I did say this way, but then I wrote increasing. It should be decreasing. You can take Rn decreasing to x, then g of Rn will converge to g of x. Okay. Okay. That's about exponential random variables. Then our next example, we have already seen this, of course, which is you take fx equal to e power 1 by square root of 2 pi sigma e power. I mean, with mean 0, it's a normal random variable with mean 0, x square by 2 sigma. Okay? Sigma doesn't matter. A sigma greater than 0. And this is a normal with this follows normal with 0 sigma. Normal random variable with 0. This is the density of normal random variable with this. So suppose x follows normal with 0 sigma square. We want to compute x square, distribution of x square. we already know the formula. If x follows, x has the density, I mean, x has density. Yes, we have already done this. Then square has density 1 by square root of 2x f of x plus f, I mean, f of square root of x, f of square root of minus, f of minus square root of x. Okay? We already know this. So we just write that x square follows. So here, I mean, f of root x, f of x and f of minus x are same for normal. It's a symmetric random variable. Okay. So we will get 2 times that. That 2 will cancel with this. So we will get only square root of 2 pi x sigma and e power minus x by 2 sigma square. This is the f square. Equal to this. Okay. The density, if x follows normal 0 sigma square, then the density of x square is this by whatever we have done earlier. We have computed that. Using that, we have this. Okay. So generalize this, and the generalization of this is what is called gamma distribution. So for that, we want to consider the following function. This is the density. We want to first consider x alpha. So if here we have a x power minus half, and e power some lambda times x. That's what we have. So x power alpha minus 1 power minus lambda x. Okay. Consider this. This is not, I mean, this integral may not be 1. So for something to be density, integral has to be 1. So we have to compute this integral. This is an integrable function. Integral, this is for x greater than 0. At 0, it is equal to 0. Then integral of 0 to infinity dx is finite. Can you see that? That's because, see, if you have, I mean, you can partially, this is alpha has to be greater than 0, and lambda has to be greater than 0. Okay. So when alpha is x power, when alpha minus 1 will be greater than alpha, I mean, it's, yeah. I mean, alpha, this doesn't matter. At near infinity, you can partially integrate it, and you will get, I mean, do you need partial integration? If you, yeah, you can, I mean, yeah, I mean, this goes to 0 as x going to infinity, but that is not enough. You have to prove that the integral, if you partially differentiate, what will happen? X power alpha. I mean, if you take any polynomial, multiply with e power minus something, that is integral near infinity. Okay, any power of x. That's because you can partially integrate it. You can get. I mean, if it is integer, you can get rid of this. Otherwise, you will get something 1 by something, but that's also near. I mean, near infinity, you can integrate it. Okay. Near 0, this is 1. At 0, it is 1. And when 1 by x power something, where that something is less than 1, something is less than 1, this is integrable. Because when you integrate it, you get the alpha plus 1 on the top. So that is also 0 at, if you integrate x power some beta, you would get x power, I mean, you will get something which is positive. You will add plus 1, so it will be positive. So because of that, you can integrate it near 0. Okay, so the bigger alpha minus 1 we have, so it's integrable near 0. Other than that, you don't have to worry because it's a differentiable function. Okay. In any, I mean, any interval which is, I mean, any interval, a is strictly greater than 0, b is something less than infinity, not infinity. This is integrable. That's because that's a differentiable. I mean, that's a nice function. You can just come. You have a. I mean, it's a nice function. So it's a continuous function. Okay, it's a bounded continuous function. So you can always integrate. Okay. Only at infinity, only at 0, you have to worry. Because of this alpha, because this is, I mean, this will be strictly greater than 1. This will be, I mean, if you take 1 by, I mean, even if when it is alpha is less than 1, it will have it's something x power beta, where beta is strictly less than 1. Okay? Because of this is integrable near 0. At infinity, this times anything is integrable. Okay? So this is integrable. This is clear. Okay, you convince yourself. Okay, this is integrable. This is an integrable form. Okay. So then, yeah, that's what. So I define this gamma of alpha equal to no, lambda we will take it out. Only this is called what is called gamma function. Alpha here. Okay. So this is equal to x power alpha minus 1 e power minus x dx. You call this as gamma. This is what is called gamma function. I mean, there is no nice form for this function. Nice form means something familiar to us, like log or sine, something like that. There is no. This is a function of alpha, and its value at alpha is this. Okay. So this is what is called alpha. And then what we have is then integral 0 to infinity of alpha lambda dx. This will be, you need to substitute lambda x equal to y. So let me y power alpha minus 1. Then we will get a lambda down here, 1 power lambda power alpha minus 1. But we will get another lambda because of this. Is that right? Yeah. Just this is equal lambda power, gamma alpha divided by lambda power. Yeah, I think so. Yeah, I forgot. Then I was uploading it. Then I realized that the midterm solution is there. You submit and then after the solution. I created. There was no mail. I created it. It doesn't send mail for that. I think. Only if I announce something, it sends the mail. Yeah, this weekend. Okay. So if you have f of alpha lambda x equal to, where gamma alpha is defined by the, for each alpha it is defined like that, then gamma lambda alpha should be on the top. Lambda alpha by gamma alpha, okay, times into e power minus lambda x. Okay, this is the density of what is called gamma distribution. Okay. I mean, if a random variable follows gamma distribution, if its density is given by this. Okay. We have proved that this integral, I mean, if you integrate it, you get the inverse of this. So, okay. Use this form. Oh, why? You should remember this. I mean, it is just to remember these things, we are writing it like this. This is gamma function. Once you remember this, you can write it. Okay. Okay. This gamma alpha satisfies. I mean, first we have gamma of alpha plus 1, okay, equal to gamma alpha times gamma of alpha. Maybe call it time. This is by integration by parts. Okay. Gamma of alpha plus 1, if you have that formula, if you have that integral, it's just equal to integral 0 to infinity x power alpha e power minus x dx. Right? Now this is just equal to, let me just write here, alpha times x power alpha minus 1 e power minus lambda x dx, integral 0 to infinity. There is something here, but that will, because of this x power alpha minus 1, that will vanish at 0. Because of this, it will vanish at infinity. Okay. So that this is just 0. Okay. We will only have this, and you will get a minus sign. Once again, there is no lambda. I'm sorry. There is only minus 1 you will get. Okay. And there is a minus of this. I'll put a minus here. Minus of minus of this. Okay. And that is just alpha times. You have alpha times. I mean, just do integration by parts, you get it. Okay. Gamma of alpha plus 1 equal to alpha times gamma of alpha. Okay. And notice that gamma of 1 is just 1. This is e power minus lambda x. If you integrate it between 0 to infinity, it's 1. It's 1 at 0, in 0 at infinity, e power minus x. If you integrate alpha equal to 1, it is e power minus x. If you integrate it between 0 to infinity, it is just 1. Gamma of alpha is 1. So gamma of n will be n minus 1 factor. N minus 1 factor. Okay. And gamma of half. To compute gamma of, let's not work it out. But because we have, I mean, it comes through the normal e power minus x square, those integration. But here you have something. Here you have this. That is why we did this. We know that this is a density. Because we got it from, we know that this is a density because we got it from normal random variable, and using that whatever the transform, we got this. So this is indeed a density. Okay, and this is just the random variable minus half, and lambda equal to 1 by 2 sigma square. Okay, so you sigma, get rid of 2 sigma square equal to 1. Yeah, it is just alpha equal to half. Sorry, alpha should be greater than 0. What I said is this, I mean, x power minus half, so it should be half, correct? Okay, so this implies gamma of half to be square. From this, we don't, I mean, if you want to compute, you have to compute something and do, I mean, you can compute it directly, but we have already done the computation for normal random variable. From normal random variable, we got this, and because of that, that's why I wrote this. Okay, and anyway, this distribution is what is called chi-square distribution. Whatever this distribution is, what is called chi-square distribution. I mean, if x follows normal, x square is what is called chi-square distribution. Okay, we know the density of chi-square distribution, which is just a special case when alpha equal to half, and then provided this lambda is 1. Okay, so then it is just gamma of half is equal to square root pi. Okay. So from the computation, from whatever we have done, it follows that we don't do it again. Okay, if you want, you can do it again, but we get that gamma of half is equal to square root of pi. Now gamma of, so now we have n is odd. If n is odd, okay, then gamma of n by 2, you want to calculate. Gamma of n by 2 will be n minus 1 is even, n minus 1 by 2, n minus 3 by 2, n up to 2. It will come. So it will come like n minus 1 by 2. N minus 3 by 2, whatever, if it exists, up to 2 into square root of pi. Right? Huh? Okay, I didn't hear what is the question. Anyway, doesn't matter. It's okay, that's not necessary. Okay. So gamma of half is square root of I. From that we can compute n using this formula. Gamma of alpha plus 1 is alpha times gamma of alpha. Okay. Gamma of 3 by 2 you can, what? So gamma of n by 2 will be n minus 1 by 2 gamma of n minus 1 by 2. It goes on like this up to this. So it is just gamma of up to 2 into square root of pi. I mean, this is into not divided by square root of pi. Okay. If you want, you can write it in the nice form. This is n minus 1 by 2. No, is it? No. This should be n minus, this right? No? 2 by 2. No. If you minus 1, it will be n minus 2 by 2, right? No, wait. n by minus 1, which is n minus 2 by 2. N minus 2, sorry. This is right, no? N by 2 minus 1. So this is right. Yeah, sorry, this is this. So it will come up to 1 by 2, right? 1 by 2 into square root of 5. This is right. Okay. Yeah. I am also getting confused, but it's okay to get it right after some time. Okay. This is what is this. We want to write it in a nice form. Okay. So this is, of course, n is odd, n minus 2. These are all odd numbers. Okay. We want to write it as some factorial. So we can insert, there are, how many 2's are there in the denominator? There are n minus 1 by 2, n minus 1 by 2. Okay. So we insert again some n minus 1 by 2 another things. We can write it like this, n minus 1 by 2, n minus 2 by 2, like this up to half. Okay, we insert the even terms also. Okay. So then you have to multiply by this. So yeah. Let me write it and then justify it. Okay. So we get those many terms. So we have n minus 1 by 2 terms here. We are again inserting some 2 power n minus 1 by 2 terms. So this will become 2 power n minus 1. Okay. So I write it on the top. So then we are inserting those terms. So this will become n minus 1 factorial. Okay. And we have got, wait. Huh? There is no 2n. We are just computing the number. Wait. Then there is something here. N minus 4 by 2. Yeah, we have inserted something. So that is precisely, but they are even numbers. So n minus 1 by 2 factorial. Okay, now it's clear. We have inserted this terms on the top. Okay. So, but they are all even numbers. So you can, n minus 1 by 2 is an even number. So n minus 1 factorial. So n minus 1 factorial, then 2 power n minus 1, then square root of pi. So this is the answer. Then gamma is this. When alpha is half integers and integers, I mean non-negative integers and non-negative half integers, we can compute it like this. Otherwise, it's not nice. Okay. Otherwise, I mean, it's still compute. I mean, it's still a number. There may be some table somewhere. You can look at the table. But for our working purpose, we will look at these things. Okay. Gamma of integer and gamma of half integers. Is the answer. There is something we will notice and we will use it later. That is when alpha equal to n. When alpha equal to n, okay, then we want to compute the distribution f of x. That is equal to alpha equal to n. We consider the gamma alpha lambda. Okay. Alpha equal to n. Alpha is an integer. That's what. Okay, maybe I can write it here. Gamma of n lambda. Okay. Suppose x follows. X is a random variable which follows gamma of n lambda. Okay. So alpha is n. Then f of x, the distribution function, which is equal to this 0 to x. Okay. Then we should have lambda power n divided by gamma of n. Okay. This is the constant in that. And x power n minus 1, right? N minus 1 e power lambda x dx, maybe y dy. Okay, right? This is the okay. You partially integrate it. Okay, then what you get? So x power n minus 1 will remain as it is. Huh? So y to the power. This is always I'm getting it. Okay. So okay, y to the power n minus 1. Y will remain like this, 1 minus 1. And this will become e power minus lambda y. By lambda you will get. So this will become lambda power n minus 1. Okay. And there is this gamma n, which is just n minus 1 factorial. You know what is gamma n, which is n minus 1 factorial. Okay. This is between 0 to x, right? Whatever. Then minus integral 0 to x. So we will get n minus 1. I mean, n minus, let me just write it. Y power n minus 2 we will get. E power minus lambda y we will get. And we will get lambda, there will be a lambda here. So that I'm writing this. So here there is a minus, of course. Here minus, no? There is a minus here. Yeah. This will be a minus and this will be a plus. There will be a minus, that will become plus. Okay. You should write it and check it yourself. It's always, I mean, because I am doing it at the board, so you should be able to do this. Okay. Now 0, you have lambda power n, but you will get a lambda down when you, I mean, this is integration by parts. You have to differentiate this and integrate the other one. Okay. So you get lambda power n minus 1. And you will get a n minus 1 here, n minus 1 into this. So that will cancel with this. Okay. That's all, no? That's all. If you continue doing this, you get the following identity. Probability of x to the x is equal to, if you continue doing this, finally you will get e power minus lambda y, right? N into, yeah, gamma, yeah. Okay. So if you do this, you will get finally, I mean, you will do it n times or n minus 2 times, whatever. Finally, you will get e power lambda minus y, e power minus lambda x. If you integrate it, you will get 1. Okay, I mean, you know what you get. I mean, no, you get 1 by lambda or something. No, you get 1. E power lambda x, you will get 1. Okay. Okay. So that will be, I will just write the expression. Okay. 1 minus summation, because I know what I'm going to say. So I know the formula. Okay. N equal to 0 to 0 to m. Okay. So now that is n. So k equal to 0 to our n is that n. Okay. N. Okay. Huh? What? Up to n minus 1 or n? Yeah, up to n minus 1, right? Yeah, up to n minus 1. You are right. Up to n minus 1. That's okay. Up to n minus 1. Yeah, that's what I gave. So lambda power lambda x power k, okay, e power minus lambda x divided by k factorial. Okay. This is okay. There is no alternating sign. This becomes always plus. So if you do it next time, it will become plus, that will become minus. There is no alternating. Okay. So this says that this is equal to, so if y follows Poisson with lambda x, yeah, lambda x, okay, and the n comes from, I mean, this is not a, we will use it later, so that's why I'm proving this. Okay, so probably if we do Poisson process, okay, if you have time to do some stochastic process, Poisson process or something, probability of x less than or equal to x is equal to probability of y greater than or equal to m. N. I mean, if something, this is Poisson, if you remember, this is Poisson with lambda x. Okay. And this is the probability up to n minus 1. So if you come subtract it from 1, it is the probability of Poisson random variable y greater than or equal to n. So that's why it stops at n minus 1. N minus 1 is right. Okay? So y greater than or equal to n. That is same as probability of x less than or equal to. I mean, of course, this depends on this x, and here it depends on this n. Okay? So this is the x follows gamma distribution, and corresponding to the x, y follows this lambda x, Poisson with the lambda x, then this is satisfied. It is just something we notice. Okay, we just record it here. Okay, much time I've taken. Discuss something about exponential, something about gamma, and there is one more thing we just record here. I mean, we know that, I mean, we can actually compute the density. If x follows normal 0, 1, or 0, anything, normal mu sigma square, then we can compute the sigma x plus exponential 0, 1 is fine, okay? Sigma x plus mu will follow normal 0 mu sigma square. Or if you follow some mu sigma square, then we can compute the linear combination of a normal random variable, okay, with a constant also. We can compute it, okay. But the other way is also true. If you have some x follows, f of x also follows normal, then this f should be linear. Okay? I mean, if some other random variable, a function of a normal random variable follows again normal, if and only if it's linear. Okay, we will prove it later. Okay, but then that is not further by other distribution. For example, if x follows, we have already defined what is called Cauchy. X follows Cauchy. I mean, Cauchy, we haven't had a parameter, just a standard Cauchy. F of x equal to what it is 1 by pi into 1 plus x square, right? And you integrate tan inverse that, and yeah. I mean, if you have uniform distribution, by applying the function tan, we got this distribution. If you have uniform distribution, by applying some log function, we got the exponential distribution. Okay, I will come to this again. So here, if x follows, this is just something to notice. This is just clear, no? If you have 1 by x, you just have to, I mean, you just have to differentiate. This is a nice function, okay, and this is for x. It's not differentiable at, I mean, at 0 there is a problem. Otherwise, it's a nice function. You can differentiate in two different interval and find that if you just do, I mean, f of at x, but it will be just the 1 plus 1 by x square into x square, right? And minus sign will, no, modulus of minus, right? I mean, we have to consider two parts, 0 to minus infinity to 0, 0 to infinity. This is exactly again. What did he say? No. If you have a decreasing function or non-decreasing function, then if you have the derivative of x, then you have phi of x is f of phi inverse x times modulus of d phi inverse by dx. You will get the modulus here. So that's what we prove. So because of that, I'm taking modulus. This is not strictly 1 by x is not, I mean, you have to consider two different intervals, and the density in the two different intervals, you can find it out, and you can do this, okay? So if x is Cauchy, 1 by x is also Cauchy. So this is a proposition. In discrete random variable case, we proved that if you are given any mass function, by mass function, we just mean that the sum of, I mean, it takes only countably many values. If you take the sum over all the probabilities, it should be 1. Okay, that's the only condition. It should be positive, and the sum of all f of xn should be, I mean, probability of that f of xn should be equal to sum of f of xn should be 1. Then we have a probability space and a random variable that we prove. Okay, we haven't proved that for continuous random variable. We will prove something very, I mean, we just have to prove the existence of one random variable, which is uniform random variable. Then we, for any given any distribution function, the distribution function is just something which satisfies those four properties. The limit at minus infinity is 0, limit at infinity is 1, and it's non-decreasing. And let's assume that it's continuous also. It's I mean, for continuous distribution, it's continuous, and it's right continuous. Okay, these are the right. I mean, right continuous. We are assuming continuity, so there's no need to say right continuous. I was just testing the property. Okay, so let f be a let be a random continuous with solution. Then you use this function f of x, and 1 minus f of x. And you can apply any function to a random variable, you get a new random variable. You take this f itself and get a random variable f of x. And 1 minus f of x is also another random variable. They follow uniform 0 and 1. If you take any random variable, assume that it's continuous random variable. Okay. Of course, if it is discrete random variable, it's if you apply a function, you will get discrete only. So it has to be continuous random variable. You take a continuous random variable, that means this function is continuous. And f of x and 1 minus f of x follow uniform 0. Okay. 2 looks strange. We can consider two proofs. Suppose this f is a nice function, differentiable and other thing, then the proof is easy. Okay, if x, I mean, if x has f, okay, then f of x, the density of f of x, density of f of x, density f of x. So what is density of f of x? Which is just right. Then d f inverse of x mod of this, whatever. But this is, of course, increasing, so you don't need mod. It's positive. F is increasing. Okay, it's continuous means it's strictly increasing. Okay, df by df of x. But then this f prime of, this is here also f inverse of x, then df inverse of dx. This is just dx by dx equal to 1. This is just, I mean, this is f prime. This is just the f of f inverse. It is just the derivative of f of f inverse, which is just x. So dx by dx is 1. Okay, so instead of that phi, if you use this, then you get the density to be 1. Density is 1 if and only if it follows uniform 0, 1. Right? We will do it in another way. For this, we assume it's differentiable or something. I mean, it's we assume the differentiability. That we will do this. We will do it directly. What do we want to compute? We want to compute x with, I mean, x as a distribution f, and we want to compute the distribution of f of x. Okay, we want to compute the distribution of f of x, which is slightly odd, but you have to write it like this. I mean, maybe I was not right. We compute this. Okay, probability of x less than or equal to x. Okay, this is what we want to calculate. F of x less than or equal to x. This is, of course, by whatever I wrote is correct, but confusing. Okay. Then this is equal to So f is continuous. We assume f is continuous, so it's strictly increasing, so it has an inverse. Okay, so this is same as probability of x is less than or equal to x. Okay. But then what is this? F of inverse equal to x. Okay, of course, f is a function. Wait a minute. F is a function from minus infinity to 0, 1. Okay. Right? I mean, it doesn't take value 0, 1. I mean, it's a function into 0, 1. Okay. It may take somewhere in the middle itself. I mean, otherwise, the limit may be limit may be the 0, limit may be the 1. Doesn't matter, but still it goes inside that. So x less than, so I mean, this is for x greater than x between 1 and greater than. Of course, if x is less than 0, f of x cannot be negative. So that will be 0. If x is greater than 1, that will be equal to 1. Okay. So, I mean, this is not uniform distribution. No? If something follows uniform means the between 0 to x, the probability of this is x. That's what you have got. Any problem with this? I have a random variable which follows, which has the distribution f. Then I will consider f of x. Okay, the probability of f of x less than, this is a random variable, f of x less than or equal to x is the random variable x less than or equal to f of x. This is the definition of f of f inverse x, which is equal to, I mean, this is not always the case. This is when x is between 0 to 1. If x is less than 0, this is 0. If x is greater than 1, this is equal to 1. Okay. So this says that f is a, says that f of x uniform. Okay. And if f of x follows, I mean, if something follows uniform distribution, 1 minus x also follows the uniform distribution. Okay, it's just the other way. Okay, so it implies also minus f of x. So now we want to say that suppose you can construct uniform random variable. I mean, this is not random. You are assuming that you have a probability space where you have some random variable that follows uniform. Okay, so suppose now we go to the other way. Suppose y follows uniform 1. Okay, and f be any distribution function. By this I mean it satisfies those properties. Okay, the distribution function. It's limited minus infinity, 0, infinity is 1. It's non-decreasing. I mean, it's continuous distribution. Use the fact that it is continuous distribution. Yes, what this existence we have to prove. Yeah, this existence we are assuming. We are not proving this. This is the only. I'm just saying this is the only thing to prove. To prove that any random variable exists, any random variable with a given distribution. You have some f with some f is just some function, distribution function. Okay, then f inverse y follows the distribution f. So if once you construct the uniform random variable, okay, then you can construct any random variable with any given any distribution. You can construct a random variable. I mean, this was a fundamental question. In discrete random variable, it's easy. If you have a discrete random variable, if it takes a discrete values, countable number of values, you take the probability space to be the countable number of values, sigma algebra to be all possible set, then take the identity function that will have the mass function. Okay. Here, if you have some distribution, given that you have uniform distribution, this you have to construct. This is not easy. This one has to go through measure theory. Without that, you cannot prove it. In the sense that you have to get a sigma algebra. I mean, we have constructed the probability for all intervals for even open set. Any open set is disjoint union of open intervals. So you can construct the probability for open set. For any set, we have to construct. Okay. to have it on the sigma algebra, you take all open set and take the sigma algebra generated by that. That will be something very big. You have to get a probability, you have to define a probability function on that, right? So this is what we have. What we want to do is following. If f is some distribution function, that is it for those properties, then we want the omega, then we have to have a sigma algebra, then we have to have a probability measure, and a random variable from x from omega to r, such that x has the distribution function, such that of x of omega x equal to, this is what we want to construct. Okay? We always assume a probability space on the background, but we haven't constructed this. To construct this, it's enough to construct the uniform random variable. Once you have uniform random variable, then you take f inverse x, you get this. Okay, I mean you can use the original function itself. From omega you go to r, from r you apply with f inverse, you get this. Okay, so to construct this uniform random variable, what do you have to construct? You have to construct a probability space. You take any, can define the probability of interval is b minus a. Okay, for any interval inside 0, 1, you can assume the probability is b minus a. So if we have disjoint union of intervals, or any interval, open or closed, doesn't matter. Okay, so you can even construct for any open set, but for anything in the sigma algebra, you need to have a theorem. Okay, so that is a long theorem. Okay, it's a Carathéodory extension theorem or something. So using that, you will prove it if you study measure theory. Okay, yeah. So that is not trivial. So if you assume uniform random variable exists, then you can assume you can construct any random variable with the distribution. Okay, that's all. Okay. Now we want to, I mean, we have already defined the expectation. Okay. So we have defined expectation through the density, but then for a discrete random variable, we defined it through the probability space, not through the probability mass function. It is, I mean, if you have any discrete random variable, then it is just the probability of, it is just you sum it over all its value. It's like summation of probability of x equal to x. I mean, summation of x times probability of x equal to x. But it uses the probability space. Then I mean, it is through the probability space we define the. If you look at it, it's really clear. Okay, we define the probability. We define the expectation through the probability space. But here, if we have x has density, then expectation of x is integral minus infinity to infinity x of x. This is how we define. This definition can be justified by having another random variable, discrete random variable, which is close to this. Okay? That we can do as following. There are two ways of doing. I mean, one Riemann integration, but that's not a real justification. I have to assume many things. But instead, if you define x epsilon, you define a random variable given epsilon, you define a x epsilon. X is a random variable. You have omega to r. Okay? Then you define x epsilon at any point x or any omega, okay, equal to x of k, x of no, equal to k epsilon. If x of omega is between k plus 1 epsilon, okay, less than or equal to k times. Whenever omega is such that x of, I mean, this is whenever omega is such that x of omega is greater than k epsilon and between k plus 1 epsilon, whenever omega is that need not be a nice set. This set, omega such that x of omega is less than k plus epsilon, k epsilon. This set need not be a interval. I mean, it's anyway a probability space. Need not be a nice set. On this set, you define x epsilon omega equal to k epsilon, but still it will take only discrete values. Okay. Now you can compute the expectation of this. Okay. Expectation of x epsilon will be summation k epsilon, then probability of this set. Probability of x between k plus 1 epsilon less than or equal to k epsilon. Okay. Okay. Now you have to justify that if you take epsilon going to 0, this will be that. But then for you need a different integration. See what you do, Riemann integration. You take an interval, you partition that interval. Each interval you take a point, and then you sum these numbers. Summation over f of I, the length of the interval. Instead, you partition the range. That is the partition the range. Here you are partitioning the range, not the domain. Partition the range. Give for this is an interval with length epsilon. You partition maybe 1 by n, epsilon equal to 1 by n, you can take. There's nothing wrong. That's not a problem. You can take epsilon equal to 1 by n. Okay. So you can take it to be k by n or k plus 1 by n. Doesn't matter. Okay. You partition the range. Okay. And then you define it like this. Okay. Now this is integration basically. Integration is what is called step function. This is a step function, but this is not step function, is not interval. This is over a different set. This set need not be in a nice set. Some different set. Okay. And then you do the integration, then that limit will be the definition of integration. Exactly. And that is how this is justified. This is not for the exam, just for your information. That is how the theory is developed. Okay. So that is how this is justified. You can justify using Riemann integration also. For that, you have to assume mean value theorem, do something, and you can do it also. But for some particular case, you can do, not for every case. Okay. For every random variable. Okay, this is our expectation. We have defined our expectation. So let us compute. We have already computed for normal density. So if x follows uniform AB, then you know what is the expectation. Expectation of x is integral a to b, okay, x dx 1 by b minus a, right? Which is just x square by 2, which is just b square, a square b minus a equal to a plus b by 2. Just the midpoint. So if we have uniform, then the mean is the midpoint. Okay? Let us do it for gamma distribution. I mean, we can do it for exponential, but exponential, chi-square, all these things are special case of gamma distribution. So we do it for gamma distribution. So suppose x follows gamma of alpha lambda. Okay? Then expectation of x is integral 0 to infinity x into x power alpha plus 1 into e power minus lambda x dx. That's right. So this is just gamma of alpha 1. No, yeah, 1 by lambda. There is a lambda, no? There is a lambda. I mean, e power. I mean, you have only e minus lambda x. Lambda times integral 0 to infinity. I mean, this is just gamma of alpha plus 1. Yeah, and there is a alpha times gamma of alpha. Is there a mistake in that? No, there is there is another thing. No? Sorry, this is just lambda power alpha times gamma of alpha. Sorry, you need this constant. I forgot this constant. I forgot the constant. Sorry. This is the integral. Expectation of x is, this is the density. Without this, this is the density. Gamma, gamma follows gamma of alpha lambda means, This is the density. Without this x, power alpha minus 1, e power minus lambda x, then these constants are there. Okay. So if you do that, then you have, I mean, this is just lambda alpha. So I think you will get, yeah, you will get alpha by lambda. Is that clear? This is equal to integral 0 to infinity, okay, x power alpha e power minus lambda x dx, okay, lambda power alpha gamma of alpha. Okay. Then if you just integrate it, this is just gamma of alpha plus 1, which is alpha into gamma of alpha. This is equal to alpha gamma of alpha gamma of alpha will go. And then you need a, I mean, you will get a, you'll get what? If you, I mean, you have to change the variable here. You will get a lambda in the bottom and you will get a lambda power alpha. So you get a, yeah, you will get alpha by lambda. You will get a lambda. Yeah. You compute it, it will be, these are all just integration. Okay. This is just alpha by lambda. So if you have the, so now you can compute for exponential distribution what it meant, which is just 1 by lambda. Okay. Okay, I will stop here.